All right, so this is going to be a video, I want to say number 4. We're looking at Unit 6, Section 6. This is all about nuclear energy resources. So nuclear energy still falls into the category of non-renewable resources. So the process of nuclear energy, the way we get nuclear energy is through nuclear fission, where neutrons will strike a large atomic nucleus and then release more neutrons and heat. And then you get a chain reaction that kind of keeps on going. So if we take uranium-235, it becomes krypton and barium. And then you get more of those neutrons blocking off, hitting the uranium-235, and more krypton and barium released in this example. So overall, in this chain reaction, a lot of energy is released. So we get a lot of energy from it. A nuclear power plant just uses that heat energy, just like a coal power plant, and produces steam to turn a turbine to produce electricity. 1 gram of uranium-235 has 2 to 3 million times the energy of 1 gram of coal. And that is why it is believed that nuclear energy could be a very versatile source of energy. So a typical pellet of uranium is 7 grams, and you can get as much energy from one little pellet of uranium as 3.5 barrels of oil, 17,000 cubic feet of natural gas, or 1,780 pounds of coal. So this is a very similar process as the coal power plant goes. In a nuclear reactor, you have control rods in the reactor core. The water is able to cycle through. That water collects the heat from the reaction. The heat is then forced into a reservoir, the steam generator, where steam is produced. And then that steam goes in to turn the turbine. There's also cold water being pumped in. This is typically from the ocean. Usually you want a nuclear reactor to be near an ocean because you need a lot of cold water to cool this whole process to keep everything from getting too hot. If you lose that cold water, you will get temperatures becoming too high, the reactor core becomes unstable, and that is when you get a nuclear meltdown. So the reactor core, fuel rods, the steam generator, turns the turbine, generates the electricity. So a fuel rod is just a tube that contains the uranium pellets, or the fuel. So a fuel pellet, many fuel pellets are put into fuel rods, and then the fuel rod assembly contains many fuel rods. The control rods are then put between the fuel rods, and that is to absorb any excess neutrons and prevent a meltdown or a fire, preventing something from going out of control. So essentially, the control rod absorbs these fission products instead of allowing them to react too much. So when a meltdown happens, the fuel rods are too hot and they melt, which boils away the water because the temperature becomes too high, and radioactivity is then released. So in a normal operation, you get this to happen. In a worst case scenario, without any water, the fuel rods will overheat, and the bottom of the fuel chamber will melt through the floor. The core will then release, and you have a massive, massive problem. So to get uranium, we have to mine it. 900 kilograms of ore are needed to be mined to get 3 kilograms of nuclear fuel. So you can imagine that is not a very efficient method. It has the same negative effects of mining. The problem is there is much less uranium needed, or the big difference is that there's much less uranium needed for the same amount of electricity. So you don't actually need to mine nearly as much to get more energy. As far as where you're going to find uranium, you're going to want to label your map here, so make sure you pause it and label the map with all the different sources. We've got uranium output in 2005 as a percentage of the top producer. Canada was the top producer at 11,627 tons. So you can see that there are some sources in the northeast of the United States. There are also sources in the Mideast. In China, Australia has a large number of sources, Africa as well, Europe as well. Now, one thing that of course can happen is you can have these nuclear power plants giving a threat to groundwater, the drinking water. The reason for that is because you need water to keep the mine operation going. So this uranium mine in Wyoming has a large amount of pollution that can get into the drinking water. Now, some of the advantages of nuclear power is that there are no emissions in the production of power. Don't forget about the mining process. Obviously, the mining process has emissions, but for the most part, when we think about nuclear energy, we think no emissions, which is really a nice thing. It's also large scale. You can produce a lot of energy, and it's predictable as far as comparing it to wind or solar energy. You can keep that energy source there. It's a very predictable source. Now, the disadvantages, of course, can include nuclear accidents and radioactive waste disposal. And we'll talk about waste disposal in particular because it is important that once the fuel rods are spent, they have to go somewhere. And they're radioactive, they're dangerous, they are hazards to the environment and to people, so they have to be put somewhere safe. So we're going to look at some of the nuclear accidents that have happened and as a case study, just so that you get an idea of the times where nuclear accidents have occurred. So one of the first ones was 3 Mile Island, which is in Pennsylvania in 1979. The cooling water valve ended up being closed, so there was no cooling water around the core, which led to a partial meltdown. They had to evacuate 200,000 people. And in the area near 3 Mile Island, infant mortality and cancer rates may have been directly related, but they did increase, and it may have been directly related to the meltdown. Another case study that you're probably familiar with, if you haven't seen the documentary or I guess it's a docu-series on Chernobyl called Chernobyl on HBO. It's very intriguing. In 1986, there was a test occurring at the Chernobyl nuclear power plant, and during that test, the cooling system was disconnected and the control rods were removed, which led to an overheating of the plant and ultimately led to a major explosion and fire. There were 31 people that were killed at the time, and there were many, many more people killed later of radiation exposure. There have been great number of cancer-related deaths that have increased since this happened. Another part, of course, was that the winds actually blew the radiation from the source, which contaminated crops and milk in nearby areas. A more recent disaster that occurred was in Fukushima, when a 9.0 earthquake triggered a tsunami that caused major flooding. The flooding caused structural damage, which actually interrupted the power supply, and without the power supply, they were unable to cool the nuclear power plant. There were fires and hydrogen gas explosions, and also release of radioactive gases. 4 of the 6 reactors that were at Fukushima were destroyed, and over 100,000 people had to be evacuated. So that brings us then to the other side, where you have to do something with the radioactive waste after you're done using it. So there's high-level waste, which is used fuel rods. So fuel rods that were used for the nuclear reaction, that's high level. There's a lot of radioactive waste. Low level would be contaminated clothing, tools, and rags of items that were exposed to the radiation in the nuclear power plant. And there are also uranium mine tailings that are also slightly radioactive and are a waste. So for the fuel rods, after a time, eventually they can no longer generate electricity, but they are still radioactive. And what's important is that uranium-235 has a half-life of 704 million years, meaning it takes 704 million years for uranium-235 to decay, or for half of uranium-235 to decay, and then another 704 million years for another half to decay. So it takes a very long time. So half-life is just the time it takes for half of a sample to decay. For instance, sodium-24 will decay in 15 hours. Carbon-14, which is used for carbon dating, takes about 5,730 years. And potassium-40 is 1.26 billion years. So half-lives change based on what you're talking about. but it's just the amount of time that half of the sample will radioactively decay. So this is just an example of carbon-14 and how it is used in carbon dating. Cosmic radiation can actually cause neutron capture for carbon-14 to be formed, and then the carbon-14 is taken in and absorbed by living organisms. After the death and the burial, the wood, the bones will lose carbon-14 as it changes to nitrogen-14 by beta decay. So the decay of carbon-14 into nitrogen-14 occurs at a very specific rate, and you can actually use the amount of carbon-14 versus nitrogen-14 to determine how long ago it stopped being exposed to carbon-14, so then you can tell how long ago did it die. And that's what carbon dating kind of tells us. So we can use half-life to determine the rate of the decay and the radioactivity level at specific points in time. So for instance, in this example, we have one half-life is 5.27 years for cobalt-60. So at the very beginning, at time of 0, you have 10 grams. It'll be 5 grams after a first half-life, 5.27 years. And then another half after another half-life. And then 1.25, another half, another half, another half, over time, halving itself every half-life. So the equation that you can actually use to determine the final amount after a certain period of time is right here. The final amount is A, the initial amount A0 or A0. You multiply that by half, raised to the power of time divided by the half-life. You want the half-life and time to be in the same units. The half is the split factor, so after a half-life, 1 pound becomes half of a pound, so on and so forth. This is just a graph to show you the radiation dose chart. I'm going to zoom in for you to show you some of these, some of the doses of radiation that you're going to get. Now these are, this is a chart, so I'll read here. The ionization radiation dose a person will absorb from various sources. The unit for absorbed dose is sievert, or SV, and measures the effect a dose of radiation will have on the cells of the body. 1 sievert, all at once, will make you sick, and too many more will kill you. So we do safely absorb small amounts of natural radioactive decay. And a special note is that the same number of sieverts absorbed in a shorter time will generally cause more damage. So more sieverts over shorter time will cause more damage, but the cumulative long-term dose can play a huge role in cancer risk. So you actually get 0.05, I want to say mu sieverts, just by sleeping next to someone. Living within 50 miles of a nuclear power plant is 0.09. So you get an idea of all of these little things that we do, right? Eating a banana, living within 50 miles of a coal power plant for a year, having an arm x-ray, using a CRT monitor for a year, having an extra dose from someone, from spending a day in an area with a higher than average natural background radiation. A dental x-ray is 5. But these are small numbers. We're talking about, a very, very small number. Using a cell phone, the transmitter actually doesn't use radiation, so a cell phone doesn't have what we would consider to be radiation, so it's important to understand that. That breaks down into here. A chest x-ray becomes much larger, and you could actually get more and more. Now, this number here, remember, compared to that very small, all of this put in together, this would be what is considered to be the maximum yearly dose permitted for U.S. radiation workers. This is the maximum they can get, and it's 50 millisieverts. If we go down even more, that will relate to some of these doses that exist. So for instance, 2 Fukushima plant workers actually received 180 millisieverts, which, if you recall, in the United States, 50 is the maximum yearly dose allowed, and they received 180, which is about 3.5 times that. There's radiation worker limits here. For a 1-year dose is 50. The lowest 1-year dose clearly linked to increased cancer is 100. So you can imagine 50 is half of what is linked to cancer, so that is a safe level. If you want to see where you're going to start seeing radiation poisoning, you need about 400 millisieverts, but it does vary. Severe radiation cases, sometimes fatal, is anywhere from is 2,000 millisieverts, which is about 2 sieverts. A fatal radiation poisoning is going to be caused by 4, and a fatal dose even with some treatment is 8. If you were to stand next to the Chernobyl reactor core after the explosion and meltdown for 10 minutes, you are going to receive 50 sieverts, which is, you can imagine, compared to all of these numbers, massive. So HalfLife Math, is measured in units known as becquerel, which is the rate at which a radioactive sample decays. 1 becquerel is the decay of 1 atom or nucleus per second. Another unit of radiation is a curie. These are both scientists that were related to radiation science and nuclear science. A curie would be 37 billion decays per second. So radioactivity level of 100 curies and a half-life of 50 years, we can find the radioactivity level after 200 years. So after 50 years, the first half-life, you'll have 50 curies, the half of the original amount. After another 50 years, you'll end up at a quarter, which is 25. Another 50 years, another half of that, and another 50, another half. So after 200 years, a 100 curie sample would become 6.25 curies. Looking at that same example, we can also do this math by counting how many half-lives are in the original sample. So 200 divided by 50 is 4. So we can take 1/2 to the 4th, which is 1/16. So 1/16 of our original amount will tell us how much will remain after 4 half-lives, after the 200 years. Another example, if a material has a radioactivity level of 500 curies and a half-life of 30 years, what will it be after 150 years? So we take the 150 divided by the half-life, so we know we have 5 half-lives. We do 1/2 to the 5th power, which is 1/32. So 1/32 of the original amount of 500 will tell us that after 150 years, we will have 15.625 curies remaining. So where do we put the fuel rods? How do we get rid of them? Well, we know that for 10 or more half-lives, they will be dangerous. And if you remember, the half-life is very long. So they store them in plants and pools of water, and the water is actually a shield of the radiation. Water is a great way to prevent radiation from spreading. So this is an example of the forbidden swimming pool. So it's actually safe to swim in these pools as long as you don't go too deep. The closer you get, the more dangerous it's going to be because of how well water is able to prevent radiation from passing and spreading. This is in the What If books, and it's a really interesting book if you ever get a chance to read. It's absurd answers to, or real answers to absurd questions. But this shows you just how dangerous it really would be. You could swim around in the water and you'd be fine, but the closer you get, as you get really close, it would kill you. So water is a great way to prevent radiation from being able to move. Now, one of the risks or the problems here is that sites are running out of pools, so now they're putting them in lead-lined dry containers on land. And the way these work is they cover it in lead. Lead also prevents radiation from passing through it. But the question really comes down to, what are some solutions to permanent radioactive waste? So could we incinerate it, just burn it all? Could we destroy it with chemicals? Why not just shoot it into space or just dump it all into the ocean? The problem is there is too much potential for a large amount of radioactivity to enter the ocean or atmosphere. So this was something I stole from someone else, but they found it on Reddit. Why don't we just shoot nuclear waste into the atmosphere and into the sun? And the short answer is because it's stupid expensive, and it's stupid dangerous if a rocket blew up on a launch pad. So you can imagine how many rockets fail in launch. If that were to happen, that fuel rod would contaminate the entire atmosphere. It would be very bad, and it would cost a lot of money because it takes about $20,000 per kilogram just to shoot it into space. So another solution is Yucca Mountain, which is very, we can relate to this because we live in Nevada. Yucca Mountain is located northwest of Las Vegas. There have been 30 years of this project happening, but it has been canceled because of many protests and congressional opposition. The Obama administration ended the federal funding, so right now Yucca Mountain will not happen. The idea was that you could store it underground in Yucca Mountain, away from people, and it would be able to be safe for, millions of years. So the future of nuclear power, there has actually been an upsurge in applications in the past decade or so. Up to 5 new nuclear power plants could come online for the U.S. in the next decade. So it is becoming more popular and more popular and widely used. So that is the end of 6.6 nuclear power. Our next video will be all about energy from biomass, as well as we will get into solar energy.